Okay, I hope I'm audible. So, good evening, everyone. So, we'll be starting with the live session 2 for the week 10 of the course Digital Electronic Circuit, which is taught by Professor Kharagpur. So, I'll give my brief introduction. I am Anil Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving the week 10 assignment problems, which are similar to the assignment problems and some of the previous year assignment problems. So, that will help you in uh, solving the problems in the examination that you will be having. This is the course outline. So we have almost reached to the end of this course. So as you can see in the initial weeks, we have covered the combinational part of the logic till week 6, and then from week 7, we have started the important or the most important part, which is the sequential circuit. So in today's week lecture, we'll cover the following contents that are design of synchronous sequential circuit, which are done using Mealy and Murray machines. So I'll let you know what are the Mealy and Murray machine and how are they used, and I'll talk about the state transition diagrams, some algorithms such as algorithm state machine, which is known as the ASM chart, and some state reduction machine techniques such as nation table, and some other tables are also there. So I'll talk about them in brief and cover the numerical problems regarding the same. So without any further, let's start with a question. So this is question number one for today's assignment. So the question says, which of the following statements are true about the following state transition diagram of a sequence detector? So A is the initial state. So it is given in the question that A, and we need to check that which of these statements are correct. We'll check them one by one. So the first statement says that the state diagram corresponds to the Mealy model. So if I talk about the basics of Mealy model, the output function of uh, both input as well as the state. But here you can see the output is only dependent upon the state of the system. So it is not a Mealy model, so it is a Murray model. So first, now I'll go on to the second option, which says a minimum of 4 flip-flops are needed to implement the sequence detector. So you can see there are number of states are A, B, C, and D. So there are four number of states, and we have already read to now to count the number of flip-flops. It is nothing but we have a general relation that the number of flip-flops should be uh, lesser than or equals to 2 to the power n. So we have m as 4, which is the sorry, we have n as 4s, which are the number of states, and m is nothing but number of flip-flops. So if I put just number of states which are 4, which are less than 2 to the power m, so if when I take m equals to 2, this condition will satisfy. So number of flip-flop required are only 2. So this statement is uh, incorrect. Go to the third state. The logic sequence detects the sequence of 110. The logic detects the sequence of 100. So for a sequence detector, what we'll see is how is the sequence going, and we'll go to the final state, which is the D. So you can see we have to go from the output of 0 to wherever the 1 is present in the circuit. So this is the basic of sequence detection that we need to follow. So now we'll go from the shortest path from A to this 0 to this one whenever this output is getting 1 for a certain input. So you can see that the input is going from A to B when the input is 1. So in the first step, if I'll write in accordingly, so what is happening is state, if name the state as S1, so state, let's suppose S25 correspond to which is the state A. There is no bit is correctly decoded. Since this is the initial state. if when I come to S1, which is state B, so here you can see from 1 to B, it is nothing but 1 is getting decoded. So 1 bit is correctly decoded, and the sequence that we have till now is only 1. Similarly, I'll go for S2, which is C. So here you can see we are going from B to C here. So we are getting a 0 extra. So 2 bits are correctly decoded, and the sequence is nothing but 1 0. Now if I go from the last state, so we'll know that the third bit will get decoded and 3 bits are correctly decoded. And if I check that how it is going from C to D, it is nothing but a 0. So 1 0 0 is the correct. This is the sequence that it will detect. Uh, and it is nothing but option 4. So 3 is also incorrect. Now I'll check with the last option. The state B and C correspond to detecting the bit pattern 1 and 1 0. So we have just read about B and C. So B is sequencing detecting the sequence 1 and C is detecting the sequence 1 0. So this statement is also correct. So 4 and 5 are correct. The correct option. Okay, so the correct to this problem will be option D. I hope it is fine. Uh, any query you can write in the chat box. We'll start the next question in a minute. Okay, so now we'll start the second question, which is similar to the first. It will cover the logic again. Again, we have a state transition diagram given and A is given in the question. So now we need to check which of the options are correct. So I'll go through it again. Uh, yeah. So you can see here A is the initial state and we have to reach where the output is 1. So here it is 0 and here it is also 0. Again here it is 0, here it is 0. Be E since the output is getting 1 here. So we need to go from A to E. So again, if I check the first option, it says that the state diagram corresponds to the Moore model. So Moore model is what it is nothing but the output is only affected by the state, which is the correct here because the only the states are causing the change in the output. So yes, it is a Moore model. So the first option is correct. Now the second option says that a minimum of 5 are needed to implement the sequence detector. So again I'll go. So you can see there are 5 number of states which are A, B, C, D and E. So number of states are nothing 5. And we know that the basic formula number of states should be M, where M is number of flip-flops. This is also known as the scaling function. So if I just put n into the picture, so it will be nothing but 2 to the power m. So when m is 2, 2 to the power m is nothing but 4. So this does not satisfy. So I take m as 3. 2 to the power m is nothing but 8. So this will satisfy. So the minimum flip-flop required will be 3, not 5. So this option is incorrect. Now if I go to third and fourth, so they are saying the logic detect the sequence. So we'll need to sequence. So if I try to see the diagram properly, so let's say A is the initial state. So I'm marking it the initial state as S0, then as S1, then S2, then S3, then S4. So if I talk about state as 0, which is state A, so there will be no bit decoded since this is the initial state. I hope it is clear. This is quite basic. Then if I talk from A to B, as you can see the arrow is pointed here, so 1 is getting detected. So at if I talk about S1, so one bit is getting decoded, and the sequence it has detected till now is only one. Similarly, if I go from S1 to S2, so we have a arrow and one is getting detected also. So here bits are getting decoded, and it is nothing. Similarly, I'll write for S3 and S4. So 3 we are getting from C to D. So we are getting an additional 0 here. So here 3 bits are getting decoded, and it is nothing but 110. Now if I check from D to E, so it is nothing but a additional 0. And this is how we are getting to a sequence. So here 4 bits are decoded, and the sequence is nothing but 1100. So if we check 1000, so third is correct and fourth is wrong. Now if we check for states B and C, so it says the state B and C are corresponding to 1 and 10. So if I check that state B, let me try some different things. So state B is corresponding to 1 and state C is corresponding to 1 1, not 10. So the question says that it is 10. So this option is also incorrect. So the correct options are only first and third, which is option C. So the correct answer to this problem is option C. I hope it is clear. If you have any doubt, you can type in the chat box or you may open your mic and ask the same. We'll proceed to the next question in 2 minutes.
Sir, could you explain again?
This particular question?
Yes, sir, yes.
Okay, sure. So, see, we need to check that what is the sequence detector and what kind of machine it is. Is it a Mure machine or a Mealy machine? So, we need to check that which of the options are correct. So, to detect, what we need to do is we need to grow from the initial state to some final state. And to check the final state, we need to check where is 1. So here you can see in the whole states, the output is 1 only at this place. Will be the final state. So the transition will be from A to E to get the final state. So we have number of states as 5, which I have written, which are nothing but A, B, C, D, E. Then this 0 corresponding 0, 0, 1. These represent the inputs, and these represent the output, which are present inside the bubble, and these are the inputs, which I'm marking with the green color. Now these are the inputs. So first of all, these uh, states are only dependent upon the state. As you can see, these are not getting affected by both input and state. So this is a basic Mure machine. We'll more about Mealy and Murray machine in one of the theoretical questions, so you need to worry about it. So if we check other options which are more conceptual, so you can see here it says a minimum of 5 flip-flops is required. So we have just seen that the number of states here diagram are 5, A, B, C, D, and E. And we know that for number of states, the number of flip-flops 2 to the power m should be greater than equals to n, where n is the number of states. So I've just put on the value of 5, and so we can get these 5 states with a number of flip-flops as 5. Oh, sorry, 3. This now they are checking. They are want us to check this. Is it 1100 or is it 1000? So if I tell you the shortcut first of all, if you are trying to do the same in GATE or in any other exam, so just go to the shortest path. You will just take the shortest path from A to E, where the input is the initial state, and we are getting the output finally as 1. So the shortest path is nothing but from A to B, then B to C, then C to D, and then D to E. And whatever the corresponding input is applied is the sequence detected. So here you can see it is 1, 1, 0, 0. And if I write one by one, we are going from A to B. First of all, we have an initial state S0. So in this S0, no bit will be decoded because it is a initial state. So I have written for S0, no bit will be decoded. It is an initial state. Now if I go from S0 to S1, to B. So the sequence detected from this part, let me highlight it, from this part will only be 1. So yeah, from this part if I say, so the sequence detected will be 1. Then if I go from B, from S1 to S2, an additional one will be detected. So this one will already get detected in the previous state, and this one will additionally get detected in the next state. So the sequence that from what I've written in C, it is 1 1. And then correspondingly from C to D, it is nothing but 0. So an additional 0 will get added, so it will be 1. And similarly for E, it will be 1 1 0 0. So this is what I have written in all the cases. So S3 will be 1 1 0, and then SE will be 1 1 0 0. So according to the options, this option is correct and this will be incorrect since the sequence getting detected is 1 1 0 0. Now I'll check for B and C. What are the patterns that are getting detected? So I've written for B, it was nothing but 1. From A to B, it was getting 1. And from C, it was getting from 1 1. And the option said it is 1 0. So this is correct. So the correct options are only first and third. So that is why the correct answer is option number C.
Sir, regarding the minimum number of flip-flops, sir, we need to convert each state into its, say, A0000, and suppose EI will means assign numbers like 101. From that also we can identify if we cannot equation.
Which
Then
equation are you talking about? Which
and
equation?
number of states is 5, so number of flip-flops is 2 to the power m.
Yes. So
So if we cannot remember the equations, then we can just write many as there are states like 5 states are there, so
yes.
101, and from there we can come to know that there are 3 flip-flops required because
Okay. So we know that the number of states is n. We have already read the mod n counters. So if we need to calculate the number of flip-flops directly, so it will be nothing but is to m. Sorry, this is n.
yes, yes.
So we have given that the states are 5. So if you put the value of 5 here, so it will come around something 3 point something something. So we know that flip flops will be the lesser set. Sorry, it will come something I guess 2 point something. What is the value? 5, yeah. So it will come something 2 point something something. So we always take the greatest integer out of that. So this is known as the ceiling function. Suppose there are 9 states. So you know that 2 to the power 3 is nothing but 8. So there will we require more than 3 flip flops to cover that. So there will be 4 flip flop requirement. Actually, similarly, if I talk about let's say 11 flip flops, so we know that 2 to the power 3 is 8 and 4 is 16. So still we can do the same in 4 flip flops. Is this clear to you?
Yes, sir.
So this is how we'll calculate the number of flip flops or the minimum required flip flops. Is it fine?
Yes, sir.
Okay, so can you tell me the answer to this question? It is a similar question. Melee machine or a Murray machine, and what is the sequence detected? I'll zoom out for you.
It's a melee machine because the output is in the state.
Told you about Murray machine is nothing but when output is only getting affected by the state. So here the
Yes,
same
sir.
is happening. So this is a Murray machine, not a Melee machine. In Melee
Actually,
machine,
yes.
the output is getting affected by both input as well as state.
Actually, I get confused between the two. Actually, I use that
Yeah, yeah,
intention.
no problem. So can you tell me the sequence detector it is having? So I'll zoom in to get the options. Yeah. So I just told you the way. So maybe if you can check and tell me the answer.
11101.
Okay, so you're saying 1101, right?
Yes, sir.
Okay, so we can see for let's suppose this is S1, this is S1, this will be S2, this is S3, this will be S4, and we need to go to wherever it is. This is fine. In short now, so S0 will be A, and here no, right? If I similarly write for S1, which is B, so here 1 will be detected. Then for S2, which is C, 1 was already there and one more 1 will be there. Then same for S3D, it will be 1, 1, and then again 1. Then S4 it is E, and there will be additional 0. So it is 1, 1, 1, 0. And for final state it will be an additional 1. So S5 will be the final state. And it will be 1, 1, 0. Sorry, 1, 1, 1, 0, 1. So yeah, so this is nothing but Moore machine with a sequence of 1, 1, 1, 0, 1. Is it fine?
Yes, sir.
So can you tell me the number of flip flops here?
Sir, actually we have five clubs. No.
No, how?
Mm, sorry, I mistaken. There are actually one, two, three, four, five, six. Six states is there, and log
Yeah,
two six is
yeah, six states. You are
two,
correct.
two, three flip flops.
Be eight, so it will follow. So we will have
Mm.
only three flip flops. Yeah, it is correct. Is it fine?
Yes.
Okay. Let's move to the next problem. So yeah, this will let you know about Mealy and Moore machine more, since this is a theoretical. The following statements are true. Can you please mute your mic? Yeah, thank you. So statements are true. The first option says that the output are synchronized with the clock for both Mealy. Only Mealy machine has a output getting affected both input and state, which we have just read. So this is a Mealy machine, and Moore machine it only get affected by the state. Don't get confused by it. So the first option is incorrect. And if we check in a Moore model, it says the input affects only the internal. The output is only a function of state. So input is only affecting the internal state, not the output. And it's correct. Mealy machine it says that input affects both internal state, so it is correct. Is that the Moore model is more sensitive to glitches as compared to Mealy model. So as you can see, the complexity in Mealy model is more, since the output is function of both input and state. So this is not correct. The Mealy model is more sensitive. So if I change them, then it would be correct. So this is also not correct. So only second and third will be correct in this question. Wait, is it fine?
Yes, sir.
Okay. So maybe we can move ahead to the next question, and maybe try to. Maybe you can solve. This is quite a easy question. I'll give you maybe 2 minutes to solve it if you can try. Easy question. You just need to calculate the relation between j, k, and y. I'll give you 2 minutes. Uh, any answer?
So I think option A.
Okay, so you're saying option A. Let's check. I'll check what will be the option. So you can see this is a general combinational circuit. Sorry, algebra question. So x is here, so x will be here. Then x will be here. This is a NOT gate, so x bar will be here. So I'm writing wherever it will be x bar. And again, this is a clock. This will be one, and then this is a connection from B bar. So here it will be B bar. Then this is A. So if I write, we need to check for JA, KA, KB, and Y. So JA is nothing but X. Then if I check for KA, K is nothing but 1. Then KB is nothing but this is a, so this is X bar. So KB is nothing but X complement, and then last is Y. So Y is this B, X complement into B. And the question says that X equals to A. We'll just replace the X with A. So JA will be nothing but A into B complement. K will be nothing but 1 since it is variable independent. It will be A bar, and then output will be nothing but A bar B. So option A is the same. This is one, this is, yeah. So option A is the correct answer.
So one thing is, I have doubt that here we have while solving we are using D, but what is the significance of BN? Means N represents the previous states,
Yeah, Bn represents the current state, not the previous state.
current
So
states.
yeah, we know that whatever the state it will be there, it will be dependent upon the previous state to get the next state, right? So if we have a n state here, so the n plus one state will be here. So the significance of n is nothing but we are getting the nth state and we are converting it to the nth plus one state. So we need, since this is a synchronous circuit, as you can see, we have a single clock in both the circuits. If it has been a asynchronous circuit where the clocks are dependent upon the previous input, it would have been a complex problem. But since the clocks are getting shorted or it is a synchronous circuit, we can write directly in terms of n only. So there is no complexity in this question. Is it fine?
Yes, sir. But A we are writing as A, not AN.
Yeah. Since question says that x is a,
We
it
can
is not. Yeah. We can write also if you are getting confused. It will be fine. Since the question is demanding the value of a, so I've not written it. I've not even written the n part. If you have, so that it you won't get confused. So fine, maybe we can proceed with the problem. You can try the same. This is also a same problem, but quite complex problem. So you want to try it?
yes, sir.
Fine, you will try it. I can give you 5 minutes for that because it is a lengthier problem. I guess it will take a bit of time to solve this. So,
Okay.
shall I start solving it?
Yes, sir.
Yeah, sure. So, it is again a state table problem. So, the question says that consider the state it says that we can only use D flip flops for digital circuit. So we need to do everything using D flip flops. So the basic knowledge that we need for D flip flop is nothing but Qn plus 1 is D. That is Qn only. So this is the characteristic equation of D flip flop. And it says that X is the input, Y is the output, and B and A are the states. So what is the correct relations between all of them? So for this, we have a diagram. So first we will make the state table. State table, since we have four states, namely A, B, C, D. We will write the states, sorry, A, B, C, D. And we'll write the next state. We'll have two inputs, x equals to 0 and x equals to 1. And correspondingly, we'll write the output for same x equals to 0 and x equals to 1. So this is the format of the state table that we use. So now you see that from input x equals input x equals to 0, what are we having? So you can see here the input is 0 and we are getting from A to A back. So for x equals to 0, we are getting from A to A and the output is 0. Is this step clear?
Um, Actually, x is equal to 0.
Yeah, for x equals to 0, we are getting from back to A and the output is 0. So I have just written for x equals to 0, we are getting from A, which is the present state, to the next state, which is A, output is 0. Is it fine?
Yes, it's fine.
So now if you check the, we are getting from A to B, it is 1 and output is 0, right? We are getting from A to B when input is 1 and output is 0. Is it fine?
Yes, sir.
Okay, so I'll write the B for some difference. So from B, we are getting from 0, 0. So when input is 0 for B, we are getting to A and the output is 0. We are getting to from B to C when the output is 0. Is this step fine?
Yes.
So similarly, I am writing for C. So we are getting D when output is 0 and the output is 0. And we are getting from C to C when output is 0 and input is 1. And similarly for D, I'll write I'm getting from D to A when output is 0, it is 1. And I'm getting from D to B when output is 0. So this is the state table. I hope it is clear.
Yes, sir.
Yeah. So now from the state table, since we know that we can only use the D flip flops, so I'll try to write the equations for the same. In D flip flops, what we will have the input. We can have certain inputs. We will have some B and N since we have A and B. So yeah, first of all, we have four states, right? Four states implies how many flip flops? Can you tell?
Two flip flops.
Yeah. So that is why we are taking two inputs, two flip flops, which are nothing but DB and DA. Let's suppose. So for the corresponding, sorry, for the corresponding the nth state, we will have some nth plus one state. So and then we'll write the DB and DA and finally take the KMF out of them. So we can have n number of combinations. Uh, we will have eight combinations. So what we are doing, we are marking states from different colors. So we'll take this 0 0 as A, this 0 1 as B, this 1 0 as C, and this 1 1 as D. So these are the states that we will have, and again it will be A, B, C, D. Carefully now. So it says the state is A, and when the input is 0. So if we check from the state table, The state is when input is A, to A, right?
Yes, sir.
So we'll write the A here again. A is going back to A when the input is 0, right? Similarly for
Yes.
B, the input is 0. So B is going to A. So again I will write the A. Then this C and the input is 0. So C is going to D. So D is nothing but 1 1. And then this D is going to A, which is again 0 0. Is this step clear?
Yes, sir.
Now the input is 1 and we have a A state. So A is going to B when the, so B is nothing but 0 1. Then B is going to is what, 1 0. Then C is going to again, sorry, then C is going to again C. So C is what, again 1 0. And then in the last D is going to where? D is going to B. B is nothing but 0 1. So we know that in flip flops, sorry, in D flip flops, I just told you Qn plus 1 is nothing but D. So we can write DB as nothing but Tn plus 1 and this A as An plus 1. So we'll repeat this again, 0 0 1 0, 0 1 1 0, and then 0 0 1 0 1 0 0. Is it fine till here?
Could you repeat, means if we considered that B and AN as four states A, B, C, D, and
Yeah.
we are using inputs. So,
0 0 is A, 0 1 is B, 1 0 is C, 1 1 is D. So A and the we have a state A and the input is 0. See, we have a state A and the input is 0. So we will go to A in the next state, right?
okay, okay. Yeah.
So this, yeah. So see for some other combination. So let's suppose this one. We have a B and input is 1. So we have a B and we have an input 1. So we'll go from B to C.
C.
So C is nothing but 1 0. So I've written
Uh,
1 0 here.
okay.
And then D is nothing but in D flip flop Qn plus 1 is nothing but Q. So I've written the Bn column here and An column here. And there is one more thing which is Y, I guess. Output. Output, we also need to write the output. So output will write on the basis of the states that we get. So for A, we are getting the output as, okay, I forgot to write the output correspondingly. So I'll let you know how it is getting. So you know that A and 0, we are going back to A and the output is 0. So I've written 0 here. Similarly for B, we are, and the output is, input is 0. So we are going from B to A and the output is nothing but 0.
Output will be zero in all except uh,
Yeah, this one, except this, when
when
D is going to A, then
yes, D is going to yes.
yeah, so where it was, I guess this is, D is going to A here. So it will be 1 here and rest it will be 0, right? So now we'll make the K map to get the relation of DB with respect to input is nothing but X, AN and BN. So I'm making the table. Okay, let's try to make it here. So we'll have a X bar X here. Then we'll have a B bar A, B, sorry, BA and then BA bar. So if I try to find out dB first, so it will be 0 0 1 0 0 1 1 0. So 0 0 0 1 1 0. So we will have this and this. So dB will be nothing but A bar B plus this is nothing but X B complement A. Is it fine?
Yes, sir.
Similarly, I am making it for DA. So DA will be nothing but this line 0 0 1 0 1 0 0 1 0 0 1 0 0 0 1. So there is no pair, so we need to write the equation for everything. Uh, so this is x complement b a complement plus this is x b a and the last term will be x B complement A complement, and the output Y we have as only a single state as one, so we can write directly this is the one. So output will be nothing but X complement A B. Is it fine?
Yes.
So we can check the option now. So sorry, D A was X complement B A complement plus X B A, X complement B complement A complement plus X B A plus X complement B. Yeah. So D was this, Y was we have just calculated X complement B A, and DB was A complement B plus X B complement A. So this is, so option D is the correct option. Is it fine?
Yes.
Okay. So maybe you can look into the question, this table again. We'll start the next question in 1 minute. Sorry, this is quite important question because it involved a lot of concepts. Grab it as much as you can. So it requires a knowledge of state table. Then we need to make the, and all of them. Then we need to make the K-map to get out the relations. Okay. We can maybe, shall I proceed?
Yes, sir.
Yeah. Fine. Go. Yeah. So this is again a state table. So first of all, you can directly see that the output is dependent upon the state as well as the input, right? So these can tell that
Mood.
these are Mealy machines.
Yes, medium machines. Yes.
Since the output is dependent upon the input as well as the state. So the first option is correct here. Now we need to check that the number states can be reduced. So reduced, it has a certain method to reduction. So we'll do that now. Uh, Give me a moment. So okay, I'll proceed directly. For the reduction, we need to check that if we are having some same states again and again. So first we need to check that where are we having the same output. So I'll mark it with the same pen. So we are having the same output 0 1. Here we are having 0 1, right? And then for all these four cases we are having, sorry, for all these four cases we are having 1 0. For the same outputs, now we'll check that if the transition is also same. So the present state, which is E, it is A and F when the output is 1 0, and this G, it is A and F when the output is 1 0, right? Is this step clear that these columns are same? Sorry, these rows are,
Yes.
so we will merge them. So this is a reduction technique which is known as row elimination. So we'll merge this E and G, and wherever there is G in the table, we'll just replace it with G. So I'll make the table again. Okay, this is the present state, this is the next state, this is the out, and we have equals to 0, x equals to 1, then again x equals to 0, 1. So present state, okay, so I'll write all of them as same A, B, C, D, and I'll merge them both. So this is A, B, C, D, then E I'll write and F I'll write. So this I'll write same again. F, A, B, E, F is nothing but A, F, G. Sorry, this is one. Okay, so I've just written the table without the G column. Is it fine till here?
Yes, sir.
And wherever there was G in the table, so I'll just replace that G with the E. You agree with this? Because we have merged these columns. So wherever there is the G, we'll replace that with a E, right? Is it fine?
Yes. So what is means if we replace the G with E,
Yeah,
so we are having one state uh, having one state less.
yeah,
So
yeah, exactly. So we are reducing the number of states if we can, because these are getting repeated again and again. So this is a method known as row elimination, in which we reduce the number of states and we get less number of flip flops and we save computational time.
this means basically we need to go from, if suppose if I A B C D E F are nodes, and
Yes,
if the means path is same in both the is
yes.
same, so we can superpose them.
Yeah, so we can reduce the number short. We can reduce this state diagram, whatever it will make, to lesser number of states. Whichever is the shortest part will make the state diagram out of it.
Yes, for we need to have both the next state and output
Yes,
matching.
exactly. We need to have a complete state table for that.
Okay.
So this state table is getting converted to this. So now here you can see these two. Since I have replaced this D with E, so this column F, which is EF10, and this D. These are again getting merged, right?
Yes, they are
So I'll
getting.
remove this F and I'll take this D, and wherever there is F in the question, I'll just change it with D. Is it fine?
Yes.
So yeah, if I try to do it, maybe I'll write it small e. Then we have A B C D A D 01 0001. Then D I'll write same E, and wherever there is F I'll change it with D, and E was again D. Then this is 10. This is 10. Is it fine?
Yes, sir.
So I guess there is no repetition now. So here it is AD, here it is AD, but the output are different. So we have reduced this to 5 number of states. Initially there was 7 and we have reduced it to 5. So the option second says that the minimum states are 5 and 6 says that it is 6. So second is correct and third is false, right?
Yes, sir.
Now the fourth option says that D, E and G are equivalent. So we just checked that D and what was equivalent? Sorry, here. E and G were equivalent, right?
Yes, E and G and are very equivalent,
E
and
and G and E were equivalent, and then in the next step,
F they are very equivalent
D
for.
D and E was equivalent, right? So there are two equivalents in this: E and G, and then D and F. But the option says that D, E, and G. So this is incorrect, and D and F are equivalent is correct, right? So the correct answer is one first second, which is option C. Is it fine?
Once more, sir. First of all, we means saw that E and G are equivalent state,
Yeah.
and
So for the
after
first case, you can see that E and G were equivalent, right?
yes, yes, yes,
So after that equivalence, we have got this table, right?
yes,
And we have replaced the G with E everywhere.
yes,
So now when we check that E and F are equivalent, right?
yes,
They are exactly. So from the second part, we have got that D and F are equivalent, and from the first, we have got E and G are equivalent, right?
mm, yes.
And in the next, we can't see any equivalent state, so we have reduced it to the minimum number of states. So there are only two equivalents in this: D and F and E and G, right?
Yes, sir.
So the option says that state D, E, and G are equivalent. It is not true, since only E and G are equivalent. But option last option says that D and F are equivalent. So this is true, since D and F were equivalent, right?
So, but when we okay,
So
DNF
we need to check the table. Like from this table, we see that E and G were equivalent, and from this table, D and F. So we will not merge them.
Got it. And
So
suppose if we see that suppose F and G are equivalent, hypothetically, if I'm saying, and that F is again equivalent to E. If we solve and we got that,
no. So you just said that F and E are equivalent, and then that F is equivalent to something else, right?
yes,
So when F and E are equivalent, so this F will get eliminated, na? You cannot proceed it further, right? Here, see, you can see E and G were equivalent, so this G will get eliminated at that time only. So we will not G is equivalent to anything else or not. We will just check for other options. Are you getting the point?
yes, sir.
Yeah. So that is why D and G are not equivalent. E and G are equivalent, but we cannot check it for D. Cannot check it for D. Yeah. So I hope you understood. So we'll start the next question. Maybe you can try the next question. It is the similar question. You have to do the same with this question. I can give you 5 minutes. Is it fine?
Yes, sir.
Okay. Okay. So any answer?
At first we are getting A and F equivalent, and the next step we are getting B, B and B and C state they are equivalent.
Okay, okay, I'll check. Wait.
But
Mm,
according to options, there are more also, the like BCH,
yeah,
BCH.
I'll. Okay, wait. So, yeah, AFEI. So here you can see what is happening. We'll check that what are the equivalent state. First of all, this is 0 0, this is 0 0, this is 0 0, and this is 0 0. So I'll mark them. This is 0 0 output. This is 0 0. This is 0 0. This is 0 0. This is 0 0. This is sorry. This is not. So here you can see what is same. A and F are same, right?
Yes, sir.
Okay. Okay. So yeah, here there is a twist in the question. So we know that here A and F are same. So when they will be same, I'll eliminate this column, right? And this F will get changed to A, right?
Yes, sir.
I'm not writing it. You are getting the point, right?
Yes, yes,
So when you will see that A and F are equivalent, and that A and F equivalent is also equivalent to this E, because EDA will be same as ADA, right? Uh, did you get the point? What I just said?
yes,
Are you sure? So A and F will be equivalent to E also. So here there will be AFE equivalence. Do I need to prove it, or do you understand?
yes. I can
You
understand.
understand, right?
Yes,
So similarly, I'll do it for the other cases. So here you can see B and CD is something C, and what is else is there? H is also there, yeah. So here you can see C and sorry, it is not same. B and C are same, right? Huh.
yes.
B
BNC.
and C are same, right? They are equivalent. So when B and C will be same, this will get eliminated, and every C will get changed to B, right?
Yes, sir.
So this now BBD10 will be same as HBD10. So B and C is also equivalent to this extra H. So BCH will be equivalent, right?
Yes, sir.
And then again, this D and G are equivalent to nothing. So D and G will remain the same. They are unique. So the correct option is option D. Did you get the point?
Yes,
Okay, so finally now try to solve this. Oh, sorry. This is the same question and just let me know the answer. You can do it in like I can give you 2 minutes now.
Sir, option D is correct.
Which option?
D, I think.
Okay, I'll check. So I can see directly S4 and S6 are same. So once they will be same, this 6 will get replaced by 5. Oh, sorry, 4. So S4, S6 are equivalent. Then this 5 and 3 are equivalent. And rest, sorry, 3 and 5. So this 5 will be replaced to 3. Okay, then there is no equivalence. So
Option D.
S0, 1, 2, then 3. Yeah, option D will be correct. I hope you get it now. Okay, give me a moment. So let's proceed to the next question. We can do this. This is again, I have already taught the concept. So it says that there are some number of states and what is the number of flip flops required. You can take 2 minutes.
4 flip flops.
Okay, let's see. Four you are saying. So we have one, 2, 3, 4, 5, 6, 7, 8, 9 states. So 2 to the power m should be greater than equals to n. And m, if I take 3, it will be 8. So this is not true. So yeah, 4 flip flops is the answer. This will be 16. Option B is the correct answer. Fine. This was a basic question. Let's proceed to the next one now. So it says consider a Moore machine with three flip flops, one input and one output. It says determine the maximum number of branches or arrows leaving and number of arrows entering. So here we have some formula, so I'll just write them. So for the maximum number of arrows leaving, the formula is nothing but 2 to the power number of inputs. And for maximum arrows entering, it will be nothing but maximum number of states into maximum arrows leaving. So one more thing, this maximum number of states, it will be nothing but 2 into number of flip-flops, right? Since maximum number of states is always given by n. So if you need to calculate the maximum number of states, it will be 2 to the power of number of flip-flops. Is it fine, the formulas?
Yes, sir.
So
The
max,
maximum.
so
Sir,
maximum, yeah, yeah.
sir, is there any means there should be logic behind this
Yeah, yeah.
maximum arrows leaving? I can understand that 2 to the power number of inputs.
Yes, exactly. Okay, fine. I'll tell you. So we have three inputs, sorry, three flip-flops. So we'll have 8 states maximum, right?
Uh,
So every
yes.
flip-flop we can have entering flip-flop as two, right? For every state we will have two inputs we can have at max as the entering flip-flops, right? Sorry, entering arrows. Do you get it? What I'm trying to say?
No, sir, it's not.
Okay, fine. I'll tell you numerically. So here you can see there is one input. So the maximum number of arrows leaving will be nothing but two, right? And maximum arrows entering will be maximum number of states, which will be nothing but 2 into 10, sorry, 2 to the power 3, which is the maximum number of flip flops, sorry, which is maximum state, which is 2 to the power number of flip flops, and maximum number of arrows leaving which are 2. So if you do it, it will be 16. So now we know that we have 3 flip-flops. So we will have 8 states. So for a single state, maximum arrow that can leave will be 2 only, right? Because we have only 2 inputs, right?
Yes, sir.
And you can see that if we have whatever number of states, the maximum arrows that will be entering in each state will be 2, right?
Yes.
Because we have 2 inputs. So we have 8 states. So in each of the state, there will be maximum 2 entering. So if we see that maximum arrows entering, they will be nothing but 16, 8 into 2. This is how we are getting maximum states into the maximum number of arrows leaving. Do you
Yes.
understand the logic now?
Yes, sir.
Okay, fine. So maybe you can try this question. Uh, any answer?
4 flip-flops and we have 2 inputs.
Yeah,
So,
okay, so I'll do it. 4 flip-flops and 2 inputs.
yes.
So maximum leaving will be nothing but 2 upon number of inputs, which is 2. So we have 4 leaving arrows.
So in any finite state machines, at a time, if we consider one state, so we can have maximum two types of inputs, 0 or
No,
1.
no, we can have certain inputs. We can have this. This is we these 4 we can use as an input. The whatever we have read, they have that certain 0 and 1 as input. But we can have these also as inputs if we go to higher number of bits or more complex finite state machines.
Okay, so each state, if there are two inputs, then each state means the number of arrows coming out from each state will can be 4, and
Yes, yes, exactly.
and
So they the coming out will be 0 0 with some output as maybe whatever 1 0 1 with some output as 0, something like that. And for every state we will have 4 incoming arrows also.
4
Not yeah. So this will be 0 0 0 1 1 0 and 1 1. So if you will be calculating the number of arrows entering, you will be getting something into 4. So let me try to solve. Maximum entering will be 2 into number of flip-flops, which is 4, sorry, 2 to the power, and then maximum leaving. So this is 2 to the power 4, 16 into 4, which is 64. Where you know that we have 16 states, and in every state there will be 4 incoming, right?
yes.
So that is why we have maximum leaving as 4 and maximum entering as 64. So option B is correct. Is it fine?
Sir, when we say about maximum living, then we are seeing from the perspective of single state, in which 4 arrows are there, and they are going to 4 other state depending upon the input,
Yes, exactly.
and maximum entering. So maximum entering should also be 4.
Oh, you are not getting. No, 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 no. See, if you see the single state, let's suppose we have a 4 flip flops there, right? So we have 16 states, right?
Yes.
So for this on loop will have 4 transitions,
Okay. Yes.
and this can go inside with some 4 transitions, right?
Yes.
And everyone can do that, right? So
Yes.
that is how we are getting 16 to 4, not for single. So we are taking both of them as a single, what to say, single state only, not
The,
multiple. Don't
means
get
you're
confused.
taking the extreme cases.
Yeah, so we are checking it for one, that how can matlab how many we can get maximum entering and leaving for a single state for both of the cases. We are not differentiating it with some different things here. Do you get the point? Uh, Maybe you can see that then we have one input, so we have two leaving, and let's suppose we have one flip flop only. So we have two states, right? So two into two will be four. So we have uh, two states, and here you can see the maximum leaving can be one. And sorry, if I try to make it something like this, since we have only two states, so you can see here the maximum entering we are only getting two. Sorry, leaving we are only getting two, right?
Yes, sir.
And the maximum entering, this is one, and this is also counted as entering, right? And this is also counted as entering for this. So we are getting it as four. We are counting for every each and every case, not for something like what you were thinking. Is it clear now?
Yes, sir.
Fine. So let's proceed to the next question now. Okay, so this covers the ASM chart. So ASM chart are nothing but the synchronous machine chart. So sorry, it is, I guess, asynchronous. Let me see what are these. I forget the complete name. It is,
Algorithmic state machines.
yeah, algorithmic. Yeah, exactly. So algorithm is state machine. So it has certain algorithms which it follows. So it starts from here when q equals to one, when a equals to zero and b equals to one. So q will get changed to zero. Similarly, when a zero, b zero, q will be remain one. So we'll make a certain kind of a truth table out of that, so that we can check that which flip flop it is reciprocating. So I'll make the table. So let's suppose we have sorry, we have a b, we have a qn, and we have a certain qn plus 1. So I'm using this asm chart, so we will have all the cases 0 0 1 1. Okay, so here you can see when q is 0 here, and when a is 1, so we are getting the next hit. So q is 0, sorry. So let's check for a and b directly. When a is 0 and b is 1, a is 0 and b is 1, we are getting q as 0. A is 0, b is 1. So in this we are just getting 1, right? What we are getting, sorry, 0. When a is 0, b is 0, we are getting q as 1.
Sir, here when after start we are getting q is equal to 1, then it is saying whether uh, keeping a is equal to
Oh
0.
yeah, 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 fine, fine. So this is not correct. So you can see here when q is equals to 0, sorry, when it is given when a is equals to 1 and b is equals to 0, we are getting a q as 1. So a is equals to 1 and b is equals to 0, we are getting a q as 1. And one case which is left is a is 0 and b is 0. So you can see when a is 0, b is 0, we are getting again back to, okay, so we have two cases here. It is either this or this. Here it was a1 b0, here it was a0 and b0. Yeah, so for that we are getting one, right? Or I have written something wrong here. Okay, so we are never getting this 1 1 and 1 1, I guess. Yeah. So is it fine? Whatever I have written till here?
Uh, Sir, I have doubt in that. That
Okay,
when
fine.
when
So yeah,
when yes, sir.
when we will recheck. So sorry. Here you can see, sorry, when A is 0 and B is 1. So we are getting Q as 0. So 0 1, we are getting Q as 0.
So, but here Qn is equal to one before the decision symbol. Just
Okay, yeah, I get it now. Huh. So that is what I was doing wrong. Q is also involved. So when A is 0, uh, when A is 0 and B is 0 and Q is 0. So A is 0, B is 0 and Q is 0. Q is 0 is where? Then what will be the next state? Uh, okay. A 0, B 0 and Q 1. Then we are again getting back to this Qn only. A 0, B 0. Okay, fine. So here you can see for A equals to 0, B is equals to 0, we are getting again back to this Q, right? Is it fine? For A equals to B is equals to 0, we are getting again back to Q. We can write this as, let's suppose, Qn. Is it fine? This line?
yes, sir.
So for A equals to 0, B equals to 0, we are getting the Q1. So we are writing it as 0 1. When A is equals to 0 and B is equals to 1, we have directly Q as 0. We don't need to check. So whatever the Qn will be, it will be always 0, right? Because we are going directly into this state. Is this fine with you?
Yes, sir. But in the first one,
Hmm.
we are getting for A is equal to 0, B is equal to 0, we are getting Q is equal to 1.
No, no, we are getting again back to this loop. So this is a self loop. You can see we are not going anywhere with this. Here we are going just here. We don't want to go. We cannot come back here. So that is why I have written. So this is again coming back here. You can see. So this is going on and on. So next state will be the previous state only due to this closed loop. Do you understand?
But this closed loop assigns Q is equal to 1.
So yeah, it is saying when q is equals to 1, this is A is equals to 0 and B is equals to 0, q equals to 1, and then okay, so you are saying that this will also be 1, right?
Yes, sir.
Okay, and q is 1. I'm not sure about it. When q is 1, see, here the thing is when A is equals to 0 and B is equals to 0 and q is equals to 1, then go to the same state. Do you understand this? When A is 0 and B is 0 and q is 1, then go to the same state.
Sir, that Q is equal to 1 it is in rectangular box, which means assignment operator, not decision. So,
It will be like that, right?
yes, sir.
Fine. Actually, I was trying to make this as zeros, then this will directly be a JK flip flop, which is the option. But yeah, so this also you can see when, let's suppose, A is J and this is K. So when J is 0, so Qn plus 1 is 0. When J is 1 and K is 0, so this will be 1. So if there will be a 0 here, then it will be a JK flip flop or a SR flip flop, since this is not even a problem. So I'm not able to see how can we get a 0 here for this case. When A is 0, B is 0, and Q is 0. How to check this? Okay, yeah, here you can see now. So here you can see when A is 0 and B is 0, then Q is 0. Did you get the point?
Yes, sir.
So that is how it is a 0 here. Is it fine now?
Yes, sir.
So here you can see Qn plus 1 is Qn when A is equals to B is equals to 0. So if I write for J is equals to K is equals to 0, then when J is equals to 0, K is equals to 1, it is nothing but Qn plus 1 is 0. And similarly here Qn plus 1 is 1. And we are don't even, sorry, 1. And we don't even care about this. So this can be a SR as well as a JK flip flop. Is it fine? So I sorry, I forget that this is also a loop. So here from here we are getting this A is equals to 0, B equals to 0, then Q is 0.
Yes, sir.
Yeah. Okay, so let's proceed to the next problem. Yeah, okay, so this is again a basic problem, so maybe you can try to solve it. So it says that there are certain values given, so you need to just verify the relation of whatever DB and DA and let me know what are they. Since it is D flip flop, so Bn plus 1 will be nothing but DB and An plus 1 will be nothing but DA. So if you can calculate this, you will get the answers. So, shall I do it?
Give me 2 minutes.
Sure, sure, take it. Did you get the answer?
Sir, the last term of DB, sir, in which we have four inputs connected to the AND gate. I cannot understand the third line when the third line is connected.
Which one are you talking about? This one.
Yes, sir. The DB have three AND gates, and the lowermost AND gate which has four lines connected to it.
Okay, so the lowermost is this one, which is okay. The
One is
first, the topmost line is J, which I have
yes,
written here. The second line is A bar, which is this, which I have written here. The third line is this
I
I.
think J. I
The third is this I, this one, and the fourth is this, which is B bar. This X is I B N. Sorry for A plus I. Then Y is this Q G I B. So this is what I am getting. You can cross check if you are getting the same. So it is given that Bn is 0, An and J is 1. So first of all, I'll calculate Y. So since Bn is 0, so Y will be 0. Then I'll calculate X. X is 1, 1. And then I is what? I is also given. I is also 1. X will be 1. Then A I bar. A is 1, I bar is 0. So this will be 0.
sir in getting JIA, but because S X is connected X
Yeah, so
just
X is connected to this. This is getting here. Sorry.
yes, the upper AND gate has two inputs only,
No, no,
not
it is three. It is three. This, okay, you
okay.
cannot see, I guess.
Yes, okay.
This, and this. There's three. And then DB is uh, Bn plus 1, which is B 0. J bar is 0. Then J A bar is also 0. So both An and Bn, this is Bn plus 1. X is 1, Y is 0. Okay, so this is answer. Maybe you can cross verify. I'm getting C as the answer. I guess this is correct.
Yes, sir. Bn plus one and An plus one will be 0, 0.
Yes. Then Y will be JIB. So JIB, B is 0, so Y will be 0, and X is JIA. So this is 1, so 1 plus anything will be 1, which is option C.
Yes, sir.
Is that fine?
Yes.
Okay, so let's proceed. Okay, so this is a sequence detector question. Uh, it says there is a sequence detector which detects three digital inputs. So three digital inputs means 3 bits with overlapping allowed. So overlapping is allowed or detectable. I'll tell you what is this. So it is given that overlapping is allowed. So for the sequence 101 and input is this, what will be the output of the detector? First of all, it will take three at a time. You can see here. Wait. So what I'll do, maybe I'll write something like this. So input and output. So what I'll do is I'll write these as 1 1 0 1 0 0 1 1 0 1 0 1 1 0 1 0 1 1 0 1 1 0. Yeah. So what is it is having is it is taking 3 bits at a time. So first it will take these three, Then since overlapping is allowed, so then it will take these three. Do you understand the point? Then it will take these three. Do you understand this? Oh, sorry. I've written wrong. Overlapping is allowed, so I've not done that. Maybe I can rewrite. Wait. So if I write 1 1 0 1 0 0, then what is this? 1 1 0 1 0 1 1 0. So this is the input output. So what it will do, it will first take these three bits. Then since overlapping is out, then it will take these three bits. Then it will take these three bits. Is it fine now?
Yes, sir.
And
Sir,
whenever, yeah,
sir, in fact, what we read, overlapping is always there in these types of machines.
yeah, yeah. So it is saying that the overlapping sequence are detectable. If it says that it is not detectable, then we cannot do that. We need to check for the next one directly. So in general, they have this overlapping with them, these Mealy and Murray machines. So whenever there will be a 101, this detector will give a 1, else it will give a 0. So if I try to write input, first is 110, so it will give a 0. Next is 101, so it will give a 1. Similarly, next is 010, so it will give a 0. 100, then 001, then 011, then 110, then 101, then 010, then 101 again, then 011, then 110. I hope it is fine. This is 00, this is 0, this is 0, this is 1, this is 0, this is 1, this is 00. So the sequence detector will give output. I'll write some with some different things: 0 1 0 0 0 1 0 1 0 0. Is it fine? I've just written
Yes,
this.
sir. Yes,
So
sir.
the option, I don't know which is option. So 0 1, and there are two ones. I guess this is option 00, 5 times 0 1. Yeah. So option B is correct.
Yes.
Fine. So let's proceed to the next one now. So it says the statement which is not applicable to a Murray machine is. So Murray machine, we already know the output is only a function of state. So the first is output is a function of present state only. So this is correct. I mean, the question says which is not applicable. The statement is correct. The option is not correct. It requires more number of states for implementing same functions. So in Murray, we don't require more number of states, but in Mealy we require more states since it is a function of both input and state. So this is uh, because more number of states. Yeah. So since Mealy has also the input, so we require more states to implement the function. This is correct. Sorry, my bad. We will we need to have more states to get the certain output because in Mealy we have the input facility. In Murray we don't have that. So we need to have more number of states to implement the same function. Do you get this second point?
Yes, sir.
Okay. Input changes do not affect the output. So yeah, since it is a function of state only, so input change will not affect the output. So this is also correct. So I guess this is wrong. So the it says the characteristic equation output is a function of state as well as input. So this is wrong, right? It is only a function of state. So yeah,
Yes.
the correct answer is 4 to this question. Is it
Sir, the
fine?
input can be also considered as a state to melee
Input can be no,
because it requires more number of states for implementing same function. So
but
melee,
Mealy has this facility of input. You cannot confuse input with state. Input is a different thing, and state is a different thing. Here we don't have any input, so we need to have more number of states to get the same thing. but it is not in Mealy ki input will be the state also. Input is a different thing. We will have certain states, and for certain input, the next state will be dependent upon both input and the present state. Get the point?
Yes, sir.
Okay. So let's proceed now. Okay. So it says a minimum number of JK flip flops required to detect the input sequence 1010. So you know these are 4 bits, right? And for the first bit, it is always that it takes an extra bit as an initial state. So first of all, if you want to write the number of bits required, so that will be always the bits given plus 1. This additional is for nothing but the initial state, because the counter will have the initial pulse and it will not give anything, it will give a 0 as the detection. So to get a sequence of 4 bit, we need to have this 5 at least 5 bit sequence detector. Is it fine?
Yes,
So for 5 bits, can you tell me the number of flip flops?
it's 3.
Yeah, so 3 flip flops will be required, right? So option 3 is correct. Okay, so let's proceed to the next problem. Fine. So it says for the logic circuit shown in the following figure, the state diagram is. Okay, it is fine. So we'll just make the state diagram. So this is a D flip flop. So we know that Qn plus 1 will be nothing but D, right? And you can see in the picture D is nothing but Y. And Y is, this is a multiplexer. So multiplexer we will have A into X1 plus A bar into X0. And X1, X0 are given or not? No, they are not given. Yeah, they are given. X1 is Q and X0 is Q bar. So I'm just writing that. X1 is what? Q. And do you understand till here? This is just basic equation.
Yeah, so how you have equated D equals to U?
How have how I have equated what?
D equals to, sorry, Y.
So D is Y here.
Okay, feedback.
Yeah. And then X1 is Q and X0 is Q naught. So I've written X1 is Q, X sorry. X0 is Q naught. Oh sorry, Q naught means this. X1 is Q, X0 is Q dash, and then this D is nothing but Y. And Y is, you can see it is a mux, so you know that A into select line plus A bar into select line. This is not, and X1 and X naught I have substituted. So is it fine? Qn plus 1,
Yes,
is
sir.
it? So Qn plus 1 is nothing but, uh, sorry. So Qn plus 1 is nothing but A X nor Q, right?
Yes, sir.
So I'll just make the table maybe A Q and then Qn plus 1. This will be 1001, right? So this is the input, this is the present state, this is the next state, right? Is it fine?
Yes, sir.
So we'll make the state diagram. So there are two states, 0 and 1. So for the first part, okay, wait, my bad. First part, it is going from 0 to 1 when the input is 0. It is going from 0 to 1 when the input is 0. Is it fine?
Yes, sir.
It is going from 1 to 0 when the input is 0. 1 to 0 when the input is 0. Is it fine?
Yes, sir.
Fine. So it is going from 0 to 0 when the input is 1. It is going from 0 to 0 when the input is 1. Is this fine?
Yes, sir.
And then at the last, it is going from 1 to 1 when the input is 1. So the state diagram corresponding is when the state are 0 and 1, and these both are 0, and this is 1 1. Correct answer. Is it fine?
Yes, sir.
Okay. So let's proceed. So this is again a similar question. Now you see here there are two flip flops. So there will be the question earlier that there are only 0 1. So here A B C D will be nothing but 0 0 0 1, something like that. You can see in the options. So
Yes, sir.
okay, so let's try to do this. First of all, you get the relation. So SA is nothing but A bar. RA is nothing but, what is RA? RA is A, I guess.
Yes.
SB is A into B bar, and RB is what? A into B.
B.
And then finally X is A and B. Is it fine? I guess it is like that. Yeah. So yeah, let's go for the input output. Having a code. Where is that? Yeah. So we have four input states which are A, B, C, D, right? Uh, let's suppose A, B, C, D, and we will have array corresponding A, then S, P, R, B, then corresponding B. And we have a X, right? So let's suppose initially this A and B are 0 initially, because we need to write something for SA in terms of A and, so initially let's suppose they are clear. So SA is nothing but A bar and RA is nothing but A, right? Do you understand this part?
Yes, sir.
So when set is zero, similarly for this SB is A B bar, A is what? A is 0, so this will be 0, B will be 0, and then when both are 0, so this is 0, and A B. Do you understand this complete line?
Yes, sir.
Sorry. Next state will be when set is 0 and reset is 1. Why it is set is 1? This is A bar. Oh, sorry, I've written it wrong. SA is A bar and RA is A. So this will be 1, not 0. You understand?
Yes, sir.
So this will be now 0 1. So this will be 0. So I'm writing it quite fast now. A is A B bar. This will be 1. This will be 0. So this will be 1. I hope I'm correctly. No, this will be, yeah, 0 1 0 0 1. So this will be 1 0 again. 0 0 1. Can cross check. I'm not sure. This is 0 1. This will be 0, and then this will be 1 0 1. No, sorry. This will be 0 1 0. 0 0 1. So yeah, this is what I'm getting. So it says that the state diagram is BA. So we need to write BA in some sequence. So I'm writing cross verify whatever I've written. So initially they were 0 0, went to 0 1, then it went to 1 0, then it went to 1 1, and then it is again going back to 0 0. So this is what we have taken as four states: A, B, C, and D. A 0 0, then B 0 1, then C is. Is it fine?
Yes.
Yeah, so you just need to cross verify these relations if I'm wrong anywhere, but there is an option which is getting the answer. So I guess this might be correct also. So yeah, so this is it. So this was a problem from the last lecture. So this was a homework problem from the last lecture. So I'll not cover this in this lecture. This was a week 9 problem. So yeah, thank you for joining. I hope the session was useful for you. So now we'll meet same time in the next problem. Uh, so yeah, we are at the end of course. So best of luck for the exams and everything. Thank you for joining.
Sir, one doubt.
Yeah,
So
ask.
exam means we are having exam on 28th, I think, as per the notice.
Okay.
So where we'll get the admit cards actually? When will?
Okay, so this everything will get informed by NPTEL only by through email. So we are only the TA, so we don't know much about that. There will be admit card, but as far as I know, you will get it through your admit cards through emails and everything. So
Okay, sir.
they will mail you regarding the same that here's your admit card and all.
If you know it means if we have exam on 28th, so exactly how many days before we?
Maybe you'll get it a week before or 10 days before. I'm not sure about it, but yeah, you will get it way more earlier. So
Okay,
don't
sir.
worry about it. Yeah.
Okay.
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 So thank you for joining.
Thank you, sir.
Yeah.